Hello, I am Nicholas Taubert, and this is my Workshop 3 presentation of the set covering problem and corresponding greedy set covering algorithm as presented in our textbook. To start, let's go over what exactly the set covering problem is. The set covering problem is a dilemma wherein there's a whole collection of items in different sets that cover different combinations of items in that collection. The goal is to ensure each item is included within at least one set while using the lowest number of sets possible. This is a recurring problem that can be found in various forms pretty well everywhere. For example, a player making a magic deck will want to cover all the common threats in their meta with the fewest cards possible, and some cards can cover multiple threats. Or, when building a Pokemon team, the player will want to cover every type weakness and resistance and strength with as few Pokemon as possible so that they have room in their team for utility and strategy. The example in the textbook goes as such. There is a committee that wants to form a group to complete a task. There is a list of skills required for the task to see its completion. Each possible member has a different set of skills. What combination of members would cover all required skills while hiring the lowest number of people? Here is an example instance of the set covering problem as provided in the textbook. Each black dot represents an element, and each circle, labeled S1, S2, S3, S4, S5, and S6, are the sets that contain different combinations of those elements. Using the previous example, each dot would be a skill required for the committee's project to see completion, and each bubble would represent different candidates and their skill sets. Some people have overlap in the skills they have, but every skill must be present for the project to be completed. For example, if the project requires a website to be created, it will never be completed without a team member who knows how to create websites. Now let's analyze this example more closely. These are all the elements total, which are in a set called X. This would be, for example, all of the skills required to fulfill that committee's project. And here are the available set covers to choose from, color-coded for clarity. These would represent the different people, each with different skill sets. As each person has different combinations of skills, they could contribute to the project. The ideal combination, that is the combination that covers all the elements using the lowest number of sets possible, is S3, S4, and S5, 3 sets total, colored as you see here. Now, the problem at hand. How do we come to this conclusion? And how could we tell a computer to solve this? Well, the problem is NP hard, but we will go over a greedy approximation algorithm and prove that it approximates a correct solution within a small margin of the optimal solution. To start, we will use these set names. X is the set of all available elements, all of which start uncovered but must be covered by sets by the end. F is the family of all the sets that can be chosen from. C is the set of chosen set covers, and U is the set of all remaining uncovered elements, which starts equal to X, but ends empty. Here is the pseudocode for the greedy set cover algorithm. Now, how does it work? Well, first we initialize the set of uncovered elements to be all the elements, because none of them have been covered yet. Then we initialize the set of chosen set covers to be empty, because we have not chosen any yet. Then, while uncovered elements remain, we choose the set that contains the most uncovered elements, subtract those elements from the list of uncovered elements, and add that set to the set of chosen set covers. In other words, we cover sets by prioritizing the set that covers the most new elements at a given stage. Ties are broken arbitrarily. Now, the textbook does not provide a proof of correctness by means of the loop invariant method, but I believe including one will help to clarify how this algorithm works. The preconditions to the loop are that there is a set of elements, a set of covers, and that each element is contained in at least one set cover. 2 more sets are also used, one to keep track of which elements still haven't been covered, and one to keep track of which set covers have been selected. The postconditions are the return of C, the set of selected set covers that is meant to contain as few set covers as possible while still covering every element at least once. The loop invariant is that for each iteration, the set cover that covers the most uncovered elements will be selected, and the elements it covers will be removed from the set of uncovered elements. In initialization, before the loop, the set of uncovered elements is set equal to all the elements, and the set of set covers is empty. During maintenance, for each iteration, a new set in the set family is selected that maximizes the number of newly covered elements, then adds that set to the chosen list and removes the covered elements from U. Finally, at termination, once every element has been covered at least once, the set of chosen set covers is returned. So the time and space complexity of the algorithm are actually pretty straightforward. This screenshot from the textbook is basically saying that the runtime depends on the number of times the function has to loop and how many elements and sets it has to sift through per iteration of that loop. Big O, big omega, and big theta are all pretty similar because there isn't much variation from best case to worst case runtime. They change by linear amounts based on the number of elements and the number of sets that must be considered. The space complexity is minimal. There's some space used to hold the set of uncovered elements and the set of selected set covers, but no new data storage is used per loop iteration. A much more interesting analysis, however, is the accuracy of the approximation algorithm. The greedy set cover approximation algorithm returns an answer that is within this small margin, H max cardinality of S for any set in the set family F. But what does this H mean? There are several steps to this, but first we must understand what the harmonic series is, because how close the greedy algorithm's result is to the optimal result is modeled by the harmonic series. This snippet from the textbook sums up the harmonic series, that it is the summation from I to D of 1 divided by I with a base case of H0 equals 0. But this is a little complicated to digest in just one read, so we're going to go a little deeper into the harmonic series. And the harmonic series is a series wherein you start with 1 over 1, then add 1 over 2, then 1 over 3, then 1 over 4, up until the index number. Here I rewrote this in the form of code because that was easier for my brain to comprehend. It'd be written as for n equals 1, n is less than or equal to k, n plus plus, sum plus equals 1 divided by n. The textbook shows the harmonic series has an upper bound of big O log n, but this isn't necessary for the proof we're about to do. This just helps better understand the harmonic series. So to prove the greedy set cover's result is close to the optimal set cover, a cost is assigned to each element for comparison. The cost of each set cover is equal to 1 unit, and that cost is split evenly across the elements that it newly covers. In this example, you can see that even though this blue square covers 6 elements total, only 4 of them were uncovered. 2 of them were previously covered already by a previously selected set cover. Therefore, the cost of 1 is distributed evenly across the 4 uncovered elements as 1/4 each. Written in the form of math, this is shown as the cost of x, C of x, is equal to 1 divided by all the elements in the set minus the elements already covered by a previous set. It follows then that the sum of costs of all the elements will equal the number of sets in the return set of set covers, because each set in that set costs 1 unit. Because each element will be covered by at least one set, it can be assumed that, even though we don't know the optimal set of a problem, we know that each element will be in at least one set in that optimal set cover set. Therefore, we can say that the cost of the optimal cover is at least the cost of each element added together, because that is the best case scenario of each element being covered only once, and the cost can only go higher from there. Because we've now shown that the left equation and the right inequality are true, we can use substitution to come up with this inequality below, which is flipped for conventional clarity. See that because the cost of each element in the set of all elements is equal to the cardinality of the returned set of set covers, C, and is also less than or equal to the summation of all costs of all sets in the optimal set, we can set the cardinality of the set of set covers to be less than or equal to the cost of all elements in each set in the optimal solution. From here out, we're going to prove that the sum of costs of each element in the set is going to be less than the harmonic number at the index that is equal to that set's cardinality. To better understand what that means, there's an example at the bottom of the slide. See that following our example from earlier, if a chosen set covers 6 elements, 4 of which were previously uncovered, then the cost of those newly covered elements is 1/4 each. If we say that the other 2 were assigned a cost of 1/9 from the first set that covered them, we could see that the cost would be 1.222, whereas the harmonic number for a set with 6 elements is 2.45, which is considerably larger. But we are going to have to prove this works for all cases, not just this one case. Once this top inequality is proven, the entire theorem at hand can be proven. That is, we can prove that the set returned by the approximation algorithm is fairly close to the real optimal value because the cardinality of the return set will be less than that of the real set times an approximation error configuration number. To start, here are the characters that will be used. S is any set in the set family F. I is any positive integer up to the cardinality of C. Ui is the number of elements in S that have not been covered by any of the previous sets. U0 is the cardinality of S. Uk is equal to 0, and K is the lowest index such that every element in S is covered by a set before Sk. In this organization, each S covers some new element, and therefore removing one of the sets S would uncover some element. Additionally, U gets lower at higher indexes. Now, for this giant equation at the bottom, this equation is saying that the cost of the sum of each element in S is equal to the sum of the number of uncovered elements newly covered in S of I minus 1 minus the number of uncovered elements newly covered in S of I times 1 divided by the number of elements newly covered by Si. This giant denominator can actually be substituted to ui minus 1 using the inequality shown, though this changes the equation above into the inequality below through substitution. Note the direction of the less than sign. So here's a look ahead at where this proof is going. It's quite a bit at first glance, but don't worry, we're going to be taking it step by step. The u I minus 1 minus u of I can be turned into a summation in itself because that summation will evaluate back to its original form. That is, the number of elements covered at any index will be the sum of the previously selected sets. Then, the next step can be taken to say that this expression is greater than the previous because j is less than or equal to u of I minus 1 at all times since it increases by 1 per iteration until j equals u I minus 1. And the expression is still greater than or equal to the left argument, the sum of cos and s. Finally, the last step here breaks the right summation into 2 by starting the values at 1 for each instead of u of I plus 1, then subtracting the area up until a starting point from the summation. We put it in this form so that it is easier to spot the harmonic series. Once in this form, it is much more clearly visible that these two summations in the parentheses follow the same structure as the harmonic series we went over earlier, which can also be seen to the right here. We can then translate them as so into these two harmonic series, written as hui minus 1 minus hui. The summation of differences between two harmonic numbers can be simplified further into hu0 minus huk because when the summation is expanded, as shown below, every value will cancel out except those two, the beginning and end values. This can be seen below according to the summation. The first value is I equals 1, so it evaluates to hu0 minus hu1 plus hu1 minus hu2 plus hu2 minus hu3 and so forth. And these pluses and minuses of the same terms will evaluate to 0. The only terms that don't have an opposite to cancel with are hu0 and huk, which is how we reach that next step in the proof. As mentioned before, UK means that there are no uncovered elements left. So that can be simplified to the harmonic number at 0. It happens that the harmonic number at 0 is 0, which makes sense because the harmonic series doesn't start until 1 and we're given h0 equals 0 as a base case. By definition, u0 is the cardinality of S, so we can substitute the cardinality of S in for u of 0 to see this familiar face once more. With that familiar face, we bring the right side of the inequality to where we wanted it to go, showing that the cost of each element in a set S is less than or equal to the harmonic number at the index of the number of elements in set S. Therefore, we have proved that the approximation algorithm is fairly close to finding the optimal solution. Now let's apply this algorithm to the example from the book to see how it works in application. Observe that each possible set covers a different number of uncovered elements. These values have been color-coded for visual convenience. S1 covers 6 elements, which is more than the rest, so that one is chosen first. Now we are only interested in how many uncovered elements a set covers, so the values to the right change. Now, S4 covers the most at 3 elements, whereas each of the other remaining sets only covered 2. Now, S5 covers 2 elements while the rest only cover 1, so we select S5 next. Now at the end, we face a tie that would be broken arbitrarily. Either S3 or S6 will be chosen, but not S2. Notice that the returned set is slightly larger than the optimal set. This is due to the error of approximation that is found in the nature of the greedy algorithm. To summarize all that we have covered, let's go through a complete example made for the purpose of this presentation. Say that there's a police department and they want to minimize the number of officers they have on duty at a time. Each officer can handle different calls, and the department must be ready to answer any type of call. Assume each officer costs the same to hire or have on duty. Let's say these elements are the types of calls the department could receive. And these are the officers along with which of those call types they're qualified to take. Taking the approach of the greedy set cover algorithm, we will add officers one at a time, selecting the one who covers the most currently uncovered calls at each stage. Observe on the right the number of uncovered call types each officer can take. Officer S1 can take the most at 9, so we select them first and cover the calls that they can take. Now in the updated visual, we see that most officers cover fewer uncovered calls. Currently, Officer S3 covers the most at 5, so we select them next and cover those calls. Finally, we see that there are only a couple types of calls left to be covered, and Officer S5 is selected because he can take both. Therefore, the greedy set cover found that officers S1, S3, and S5 can cover all of the given types of calls. Now, to look at the cost paid per call type covered, assuming each officer is paid 1 unit that could be hourly, daily, weekly, even yearly, we find that the first officer covers 9 uncovered calls, so each job costs 1/9 of a unit to cover. Next, Officer S3 covers 5 currently uncovered calls, so each of those jobs costs 1/5 of a unit to cover. Lastly, Officer S5 is added for the last 2 calls. Because these 2 calls require a whole another officer to cover, they are more expensive than the rest cost-wise. And here are my references used to create this presentation, all from our textbook, just different sections of it. Thank you so much and have a great day.